So what about conformations of a molecule? That's what chapter 3 was all about. Different conformations of cyclohexane, different conformations of butane. What about conformations of a molecule? Can they be chiral? What if one conformation is chiral, but another conformation is not? The same molecule. It's still the same molecule. Bottom line is, a molecule can't be chiral if it is in equilibrium with a conformation that is achiral. Okay, so if it has a conformer that is achiral, it's going to be achiral. If it has a conformation that's achiral, it is achiral. Okay, so to determine whether a conformationally mobile molecule is chiral, consider its most symmetric conformation. Because again, if it can be achiral, then it is. Okay, but it does need to be conformationally mobile. Okay, so for instance, how about gauche butane? CH3, CH3. So when you make this guy with your model kit, just gauche butane, right? There's definitely no internal mirror plane, right? Versus when we make eclipsed butane, there definitely is. Right? CH3. So like right behind it, CH3, just right behind it. And so really, right, it's just cutting right through the middle is the internal mirror plane for the eclipsed butane. So here was gauche, and here was eclipsed. Right? And the gauche, then I said, was chiral. Okay, there's no internal mirror plane there. But the eclipsed is achiral. Right? Just right in between the two carbons is the mirror plane. Right in between the two. Let's see if we can make it with our model kit really quick. Right? So here was eclipsed butane. And so again, looking down that carbon, if you just cut it right down the middle, right down the middle, there's an internal mirror plane. But if you're gauche, if you're slightly altered, sorry, let's make it look like the one on there. Okay, so if you're gauche, right, then there's no more internal mirror plane. So, what did it say though? If it is in equilibrium with a conformation that is achiral, then it cannot be chiral. Okay, so this is definitely its most symmetrical conformation. Most symmetrical. As in, if you can find a mirror plane in a certain conformation, if you can, then that is its most symmetrical conformation. And this guy definitely has a mirror plane, so it is achiral. Butane, just butane is achiral. Everyone kind of knows that. Butane's kind of achiral. Okay, some harder examples. What about cyclohexane? Okay, so BR, sorry. So this BR is down, and so is this one, right? This one's equatorial, this one's axial, and it is in equilibrium, right? If we do that ring flip. Okay, head becomes the foot, so here's BR, and here's the other one, BR. Okay, and definitely when we look at them in 3 dimensions like this, they definitely both look chiral. I definitely do not see any mirror planes here. Okay, I don't see any internal mirror planes in the 3 dimensions like this. But if we think about the average, okay, because again, it's going through both of these interchangeably, right? Because one was axial and one was equatorial. They're equal in energy. So if we think about the average, it looks like the flat cyclohexane. Okay, where both of those bromines are down. Again, you're on top of the molecule. Both of those bromines are down. And now, do you guys see the mirror plane? I definitely do. It's right here. There's the mirror plane through the molecule. Okay, and so this is definitely the most symmetrical conformation of cyclohexane. If you ever have a cyclohexane and you want to know if it's chiral or achiral, draw it flat. Use the flat cyclohexane. Okay, always just use the flat. Okay, so This again is the most symmetrical conformation. And therefore, it is achiral. This molecule is achiral. Again, point being that if you ever have cyclohexane, just use the flat version. Use flat hexagon for cyclohexane. Okay? Just draw it flat. And again, if you can find a mirror plane, then you're achiral. Okay, how about one more? This one, again, is a little bit more difficult. This guy. So he definitely does not look achiral, right? I don't see an internal mirror plane here. However, if I just rotate about this single bond, this is again when a model kit will be really helpful. Okay, then I can rotate it, and what happens is that OH then becomes forward. What was going back? If I just bring that carbon up, that OH is going to come forward. And now do you guys see the sigma plane? I sure do. It's right there. Okay. So again, this guy is achiral. Because if it can be achiral, it is. Okay? If it can. And so my tip again is to practice. I knew that if I bring this carbon up, that OH is now going to go forward. How would you know that? After practice. Okay, so practice, practice, practice in terms of trying to figure these ones out. But please note that it is definitely possible for compounds to be locked in a certain conformation, okay? It can be locked. Again, these are conformationally mobile, all of these, but they can be locked, okay? In this case, you cannot consider the compound's most symmetric conformation, okay? Because it can't get there. It's locked. Instead, you must consider its true shape in 3D. Okay, so for example, there are these compounds called biphenyls, okay, which kind of look like this. If we could draw them on paper, when we draw them on paper, here's one, there's the other, BR, and let's put something down here like a different halide. Okay, so again, as they're drawn flat, they definitely look as though they have a sigma plane right through the middle, okay, but they don't actually look like that, okay, they're not flat. Instead, they kind of take this, they're not flat, okay, they're not flat. How do I draw this? They're not flat. Instead, they take like this three-dimensional shape. So when they're flat like this, that's what's going to happen. Okay, so they can't be perfectly flat like this. Again, there would be a nice mirror image, right? Nice mirror plane right through the middle there. But instead, they take this three-dimensional perpendicular to one another. The rings, they're perpendicular. And that's because they're electron clouds as well as those big old halides. They take up a lot of space, and so they just don't fit right next to each other. Okay, so it actually looks like this, and if I could try and draw some third dimension in it, okay. Okay, so this one's now coming at you, and that back part is going away from you, so this bromine then is going away, and this iodide is definitely coming at you. Okay, so again, it's not nice and flat like this, it actually takes a perpendicular conformation. Okay, so this guy is locked and chiral, therefore he is achiral. Okay, this guy is achiral, but as he's drawn, but it's impossible to make him nice and flat like this. Again, they can't be nice and flat. Okay, they're not going to be nice and flat. They're going to be at a nice perpendicular 90 degrees to one another. Okay, and that's because they're just too close. So it's impossible. Okay, so these biphenyls, they do not sit flat. Okay, so these are harder problems. The biphenyls do not sit flat. And there's one other type of conformationally locked set of molecules, and those are called allenes. And allenes are pretty much when a carbon has two alkenes on the same carbon. So this is what I'm talking about. 2 alkenes on 1 carbon, right like that. Okay, so if we drew this molecule just flat, an alene here, right? It kind of looks as though there's a sigma plane right through the middle of the molecule, but just like the biphenyls, this is not actually what it looks like in 3 dimensions. Instead, the ends are actually perpendicular to one another, just like with the biphenyls. Okay, so we have H, CH3, down with the alene, and then these guys are going to be in the plane, H and CH3. So again, instead of sitting flat, okay, again, they're perpendicular to one another. Okay, so they're not flat. So imagine these are the CH3s, they're not flat. Because right now there would be a mirror plane right in the middle, but instead they're actually perpendicular, just like the biphenyls. Okay, so there is no sigma plane. Okay, so we are actually chiral. And that's because the ends are perpendicular. Ends are perpendicular. Why are they perpendicular? How did I know that? That's because this guy is sp hybridized. So remember, right, when you're sp hybridized, you have that mirror plane, that p orbital right in the y-axis, but then you also have the p orbital in the z-axis. Okay, so it's not like right on top of each other. Okay, so if we imagine this is how the other pi bond is going to be made. Okay, the 2 pi bonds need to be made on that middle carbon. So we have 1 pi bond in the y-axis, right? But then we also have a pi bond in the z-axis. And so that's the one that's perpendicular. And so as a result, then these groups are going to be in the plane, and these groups are going to be coming out of the plane and away. Okay, so it's because of that pi bonding right in the middle, those p orbitals. One last topic, important atoms of stereoisomers. All right, a carbon bonded to 4 different groups is called an asymmetric carbon. We're going to see these in a lot of our chiral compounds, okay? And that's why they're also called chiral carbons, okay? They're often designated by an asterisk or a little star, okay? To be technical, IUPAC defined these carbons and other atoms like them as chiral centers. And so their very specific definition is that chiral centers are any atom holding a set of ligands in a spatial arrangement that is not superimposable on its mirror image. So what they mean is something here, carbon, it's got 4 different things. They're always going to have like 2 in the plane. So we have 1 group here, a 2 group here, 4 different things. I'm going to show you guys examples. Here's group 4, and then here's group 3. Okay, 4 different things. 4 different things. C is an asymmetric carbon. That's the term I like to use most. Asymmetric carbon. Okay, so for example, how about, I'm drawing it this way for effect to make it look just like that group over there, Br. Okay, do you guys see the asymmetric carbon? It's actually right here. Okay, because here's 1 group, here's a second different thing, third different thing, and here's the 4th group. And although 1 and 4 are both carbons, the 1 group is a CH3, and the 4 group is a CH2CH3. Okay, so the 1 group is a CH3, the 2 group is an H, 3 is a Br, and 4 is a CH2CH3. That's different than the CH3. So you have to like keep going to look for a difference. Okay, and so if we looked at the mirror image of this molecule, we will see that it is non-superimposable, which is why this is indeed a chiral molecule. Okay, so a set of ligands that are not superimposable on its mirror image. Okay, so again, it's right here. This carbon has 4 different things. 4 different things. Bound to C. Therefore, this is an asymmetric carbon. Asymmetric carbon. Okay, Other examples, how about even if I don't add stereochemistry, even if I just keep them as lines in the plane of the paper? Do you guys see the 4 different things here? It's really not so bad, right? We got 1, 2. Yes, we have CH2s, but then here we have a CH3 and here we have another CH2. Okay, so it goes CH2, CH3, CH2, CH2, CH3. So I will designate that with my asterisk. Again, our 1 is the OH, 2 is H, 3 is CH2, CH2, CH3, and 4 is CH2, CH3. These are different groups. You have to keep going along the chain to look for the differences. Keep going, okay, to look for the differences. Look for a point of difference. Okay, how about one more? This guy actually has multiple asymmetric carbons. Okay. Where are they? Asymmetric C's, question mark. Where are they? I have a tip, and that is don't forget the H's. Don't forget H's. Okay? Because they're always there. Right? This guy actually has 3 asymmetric carbons. We have one right here, because our 4 groups are an OH, again an H, CH3, and a CH. Another one's right here. Okay, we have a CH, a CH2CH, CH2CH2. So there's another one, and we have a third one. A CH3, an H, CH2, CH, CH2, CH2, CH2. Okay, so these are 4 different things, all bound to those. Okay. Chiral centers are examples of stereocenters, and so this is a bigger, broader term. It's more encompassing, and so it's got a more general definition. Stereocenters are atoms at where the interchange of 2 groups gives a stereoisomer. Okay, and so the one we had earlier gives us a nice easy example. Okay, remember our 4 groups, 1, 2, 3, and 4, because here was our asymmetric carbon. Is it also a stereocenter? Let's see. If we switch 2 and 3, okay, we're going to get this molecule. So the H is coming forward now, and the Br is going back. Okay, this is still an asymmetric carbon. So let's see if this carbon is a stereocenter. So it says stereocenters are atoms at which the interchange of 2 groups gives a stereoisomer. Is this the same molecule as the original? No, it's non-superimposable mirror image. So this is not the same molecule. Okay. Instead, it is a stereoisomer. Okay. Therefore, that starred carbon is a stereocenter. Okay. Again, like I said, stereocenter is a more general term. Okay, yes, pretty much all chiral, all asymmetric carbons are stereocenters, but not all stereocenters are asymmetric carbons. So here's a good example. This molecule right here, okay, right here, this carbon, is he an asymmetric carbon? As in, does he have 4 different things bound to him? Absolutely not. We have a double bond right away. Double bond means 2 to the same thing. Okay, so anything with double bond is not an asymmetric carbon. So we need 4 different things. But is it a stereocenter? Okay, like I said, stereocenter is a more general term. So if we switch the H and the CH3 on this carbon, okay, do we get a different molecule? And the answer is yes. Do we get a stereoisomer? And yes. We go from the cis stereoisomer to the trans stereoisomer. Okay, this is a stereoisomer. Okay, therefore, the C is a stereocenter. By that I mean the circled C. Okay, I meant the purple C. Okay, we will pick up next time on Monday.